Hi, my name is Jack Elston. I'm with Black Swift Technologies. I'll be presenting on the S0 UAS, a small ruggedized unmanned aircraft system capable of atmospheric profiling. Black Swift Technologies is unique in the fact that not only do we actually go and field our systems, but we've developed our own autopilot systems, vehicle design, payload integration, everything even down to the user interface. This allows us to be flexible as far as new sensors, new sensing capabilities, and new flight patterns in order to achieve some of the demanding aspects of scientific applications. The design principle around the S0 is to provide a vehicle capable of rapid profiling of the atmosphere up to 15,000 feet above the ground level, while keeping it low cost, but also returning scientific grade measurements. We'd like to do so in a format that people are used to, so the user interface will be similar to the photographs that are normally used for radiosondes, and the data formats will be available in a number of different formats that are commonly ingested into forecast models. In addition to the basic profile, the users will be provided with Black Swift Technologies' flight management system, which will allow them to perform more advanced capabilities such as scripting, horizontal profiles, or volumetric profiles with the vehicle. One of the unique aspects of the S0 is the use of 3D printing in a lot of the different components. This allows us to provide accurate things like wind measurements while keeping the construction of the vehicle relatively cheap. Here we show the results of 900 different point calibration in a wind tunnel on alpha and beta suites with plus or minus 15 degrees, where we were able to get very accurate representation of the wind field from the probe itself. Here we can see the results through the various sweeps through alpha and beta in the tunnel data, showing that there is little lag within the instrument. This shows a zoomed in representation of one of those sweeps where you can see that the measured versus true for the wind tunnel data from the raw versus the filtered output show that we maintain a high level of accuracy while introducing very little lag into the system. Here you can see flight data that was recorded aboard the BST S1 UAS, which is being used as a surrogate as we design the S0. This was made using the exact same sensor suite and a probe tip that is manufactured using the same 3D printing technologies that we envision using for the S0. Beyond scientific measurement accuracy, one of the other key requirements to making a vehicle that is easy to use for regular measurements, whether it be for operational forecasting or for research, is to provide something that's easy to launch and recover. Our requirements for the S0 is to be able to launch and recover the vehicle within 10 feet of one location. This will be done regardless of whether the site contains large, tall, vertical obstacles like trees, and so one of the design requirements has become that the vehicle needs to be able to take off and land vertically. Another key design aspect is to be able to provide measurements for as long as required. In order to perform the 15,000 vertical profiles, the vehicle must be able to fly for at least 40 minutes of flight time. While this might be shorter than some campaigns require, fortunately, the low cost of the vehicle should allow for purchase of several of them to be able to do multi-vehicle staging, in that you can have several vehicles charging while others are up flying to maintain continuous observations of the same area. The mechanical design of the S0 was also carefully considered in order to provide accurate measurements while reducing user complexity. The tip of the aircraft is integrated tightly with the avionics in order to reduce the wind measurement errors that result from alignment issues. Additionally, the user interface beyond the tablet consists of a simple panel consisting of a status LED for charge, a status LED for the aircraft readiness, and an on and off switch, a USB interface for downloading data, and a power connection for charging the battery. One of the more difficult design aspects of the S0 is the vertical takeoff and landing. We've developed a simulation environment that allows for us to design and test our algorithms before actually fielding them on the physical system. In order to facilitate transition from vertical to forward flight and back, the tail section is fully articulated, allowing for much larger control authority over the pitch of the aircraft. Furthermore, several different designs were considered for use in vertical and forward flight control. Here you see two different options, one being large flaps that were inserted behind the motors on the wing and surface themselves, the other being pivoting motors. Here you can see testing of the pivoting motors for use in determining the pitch authority on the aircraft. The user is able to use a handset to send a desired signal, and then we're able to measure that with the autopilot system. Here are the results from testing the two different methods for providing pitch control of the aircraft. On the left you can see the big flaps, and on the right are the pivoting motors. The command signal is shown in blue, and the measured torque from the autopilot is shown in red. As you can see, the measured torque on the big flaps is much lower in amplitude than desired and has significant lag. For the pivoting motors, this much more closely tracks the desired signal. Additionally, the yaw authority was similarly tested. We show here the video of recording from testing the flaps on the left and testing the pivoting motors on the right. You can see the result from the two different tests presented here. Unfortunately, although the pivoting motors provided a good desirable response in the pitch control, it has less authority in the yaw control. Fortunately, when comparing this again to standard known vehicle types, this still should be sufficient for controlling the aircraft. However, it is worth noting that the large flaps behind the motor do provide a much more responsive control surface. In order to validate our design process, a first article was constructed. While this first article was incapable of vertical flight, it did allow for us to hand launch and perform horizontal profiles in order to validate the propulsion system performance, estimated flight times, and test within strong wind fields. Here you can see video from flight testing of the first article. The vehicle is flying in approximately 15 knot winds and performing loops above the operator so as to maintain it within visual line of sight.
Like 40%. Yeah, I don't know what the range is. We should have timed this and get battery. Josh is a busy. Yeah, should I just keep recording till the end so we can get battery time?
Sure.
A validation campaign has been planned to fly the vehicle around an instrumented tower at the Southern Great Plains site. This has several different sets of instruments along the vertical axis of it. These will be used for comparison against the onboard instrumentation, and they will be compared against radiosonde launches. In addition, the team is bringing along several different other unmanned aircraft systems that would be used to compare against the S0's data.